G'day viewers. It is important to appreciate that all matter has a relationship with the quantum vacuum. Moreover, all physical characteristics of matter has a relationship with the quantum vacuum. For example, spin angular momentum has this relationship, so does mass and so does electric charge. In episode 93 and 94, we investigated this relationship in terms of particulate spin radius, so please take the time to view these videos if you have not already seen them. However, in this episode, we are going to investigate the combined spectral characteristics of mass and electric charge. We shall determine the physical scale at which the electrogravity-magnetic construct predicts that the quantum vacuum associated with the electrostatic force converges with the quantum vacuum associated with the gravitational force. In fact, we show that the quantum vacuum electrostatic and gravitational spectra converge at the yoctometer scale for charged particles and converge at less than the Planck scale for neutral particles. Similarly, we show that the quantum vacuum harmonic cutoff frequency converges at the yottahertz scale for charged particles and converges above the Planck frequency for neutral particles. Hence, the results from this episode, in concert with the results from our previous episodes, seem to imply that the origin of spin angular momentum, mass and electric charge may denote the physical scale which defines material existence. This in itself is a very exciting possibility and worthy of deeper reflection. Therefore, in the next episode we shall investigate the physical scale at which the quantum vacuum's relationship with spin angular momentum, mass and electric charge are unified, if at all, within the electrogravity-magnetic construct. It will be an interesting investigation, so I encourage all viewers to keep following our channel. Anyway, for now, let's get into the quantum vacuum spectral convergence derivation process of mass and charge. The spectral convergence derivation process commences with the selection of a physical model to analyse. Herein we shall utilise two similar fundamental charges, hence they are repulsive. However, the results we will present on the next slide are unaffected by the choice of similar or dissimilar fundamental charges. Thus, utilising equally attractive or repulsive fundamental charges does not alter the outcome. Okay, let's now walk through the spectral convergence derivation process step by step. Step 1 derives the electrostatic spectral energy density. In episode 34, we derived a relationship between the electrostatic force and the quantum vacuum. We did this in order to solve the long-standing and well-known many orders of magnitude problem. We showed that a 90-degree phase difference exists between the quantum vacuum, electrostatic and gravitational spectra. We recommend all viewers to review episode 34 before continuing. Step 2 involves two parts. The first part derives the electrostatic force density. The second part relates the electrostatic force to Newtonian acceleration via Buckingham pi theory. Please review episode 1 before continuing. Step 3 converts the resultant quantum vacuum acceleration arising from electrostatic and gravitational forces into a cubic frequency distribution utilizing Buckingham pi theory. Step 4 quantizes the output from step 3 into quantum vacuum spectral frequency form whilst obeying Fourier harmonics. Step 5 defines the ratio of energy densities for utilization in the harmonic cutoff function. Step 6 establishes the quantum vacuum upper spectral frequency limit based upon the presence and influence of charge and mass. Step 7 determines the physical scale at which the harmonic cutoff mode satisfies the condition of spectral convergence, that is, the spectral convergence factor is incrementally increased until the harmonic cutoff mode equals unity. Step 8a. Once the condition of harmonic cutoff mode equaling unity has been achieved in step 7, then the electrostatic and gravitational spectra have been unified at the associated spectral convergence radius. Please note that column 5 is arranged in decreasing order and only contains charged particles. We will address neutrally charged particles on the next slide. Step 8b, Step 9a and Step 9b are very straightforward and self-explanatory. Column 2 expresses the spectral convergence radius in terms of the Planck length, whilst column 6 expresses the quantum vacuum harmonic cutoff frequency in terms of the Planck frequency. Let's now summarize what we have learned. The spectral convergence derivation process commenced with the selection of a physical model to analyse. Herein we utilised two similar fundamental charges, hence they were repulsive. However, the results appearing on screen are unaffected by the choice of similar or dissimilar fundamental charges. Thus, utilising equally attractive or repulsive fundamental charges in our formulation did not alter the outcome. Please take a moment to pause the video and study the results appearing on screen. The depiction of the proton you see provides a useful template to describe our results. The spectral convergence radius denotes the physical dimension whereby the quantum vacuum, electrostatic and gravitational spectra converge and are unified by a single harmonic frequency mode. At this physical dimension, the quantum vacuum harmonic cutoff frequency is defined in column 6. Thus, in the case of the proton, number 1, the spectral convergence radius equals 0.33 yoctometers. Number 2, the quantum vacuum harmonic cutoff frequency at the spectral convergence radius is 10 to the 11 yottahertz. For interested viewers, you can find a list of useful references on the next slide.